Oh, no, I'm trying to do the...
And if we your stick.
Yep. I am on and off.
Mouse.
I just do it.
Half off the dot.
Except I'm aiming over there, so you can speak.
I guess would be yes. Ready to go, Jim? Well, good afternoon, ladies and gentlemen, and welcome to the UC San Diego Osher Lifelong Learning Institute. My name is Steve Clary. I am the chair of the curriculum committee here and will be coordinating this afternoon's lecture. The lecture is entitled The Strange Old World, What New Horizons Has Taught Us About the Pluto System. In July of last year, the New Horizons spacecraft successfully navigated 3 billion miles, let me say that again, 3 billion miles of space travel into the solar system to reach its target, Pluto. And this close encounter has revolutionized our understanding of this distant world and other large bodies in the Kuiper Belt. With us to explain the significance of this mission is one of our favorite speakers, Professor Adam Burkasser, Professor of Physics and the Director of the Cool Star Lab here at UC San Diego. Adam has authored numerous publications. He received his PhD from California Institute of Technology. Please join me in welcoming Adam Burkasser back to Osher.
Thank you very much. Okay, thank you very much. I'm very pleased to have an opportunity to talk about. I actually have a long history. The planet Pluto, but PhD student. This is Mike Brown. This is his book, How I Killed Pluto. And talk a little bit about whether or not Pluto is a planet or not. It's a fascinating place, and we're in a really amazing time right now because as of last year, in fact, really just about 6, 7, 8 months ago, we have suddenly learned system, things that we've never expected, things with you that have come out so far. And I should say have come out so far because we're still downloading data from the spacecraft. That's going to be continuing on until September. Now, just so I can give space telescope system ever take so small that get a sharp picture. I see world way out there. Our system look like is not too much. The Greeks saw what measure the system that and planets 1600. So those of you who are Kepler fans know the shapes that define the universe. Terrain out there is cubic shape. Now, was that I should say it was kind of our solar system. Observation in the 2nd century BC. With your naked eye. Is quite an amazing feat. Uranus has a very long orbit. Much of an orbit, but you can start to see seem to itself. It didn't follow the right trajectory. And so wobble in its orbit. his orbit to predict this other planet in 1846. Even longer. All right, its orbit Neptune will be monitored over the course of very things that don't. There's a love you. Inward to Mercury. And actually, even past that bright object with the sun, but reports in the literature inside our solar system. From many literature for all sorts of descriptions, the rate and the and new planet. Pluto. Well, who later became Venetia Fair, she was a young girl, 11 years old, in the local paper in England. The god of year-old girl. And this passed up, and this observatory to Lowell himself, naming new planet, small girl, and I think that's misspelled Viptia, for dark, gloomy planet. The name stuck, and in fact, it stuck in both. There is evidence Neptunian was named after in many realms. So great to be able to read problem. Turns out, started his program, and actually I should say toward the end of it, he was predicting it's somewhere around 7 times the mass of the Earth, which is a really big. A little tug on those planets. Now, after the movement of this little planet, predicted a mass of about 1 Earth. Gerard Kuiper, and Kuiper will come up again later on as we talk, brought that down around Pluto, which I'll show you, because the moon gravitational pull and basically an extension of Kepler's laws. And that brought that all the way down to 1,000th of an Earth mass for this thing to pull. It turns out that that perturbation of Neptune wasn't solved until 1992. In 1989. By 0.5. His mass solved all the problems. So Pluto was an asteroid. This happens a lot in astronomy. All right, now I mentioned the estimate of the mass came with the discovery of Charon, the moon. Not that spectacular, worse than the Hubble Space Telescope images, but still pretty tough to see. The moon is actually this bump on the blob here, and that's the blob without the bump, and that's, of course, with Charon. Actually, the observation that proved that this was a moon, that it would disappear and reappear as it orbited around the planet. And by making careful measurements over the course of the 6.4-day orbit of this system, they were able to measure the mass of Pluto and Charon combined, and then for the masses of each separately. This is 1978. Now, that's not the only moon around Pluto. As satellites were found in, these are we had these 2 new satellites discovered in 2005, and then after that, and very recently, 2011, more tiny little moons, that's Kerberos and Styx, were also found around Pluto. It's passed by be the first time we get a close-up picture of moons that we haven't even predicted. Planetary system. Be back in 1915, it's still pretty good size, and all sorts of moons going around. It seems like the question, is it a planet? Why I have that answer, and why my advisor did as well. So when we look at the orbits, really stands out is Pluto. All the other planets orbit in these very nice, almost perfectly circular, and importantly, very Newton's law require planet. If you look at the comet, planets all seem in nature was really the driving force for what's known as the solar disk model, the sort of nebula model for the evolution or the formation of the solar system, that the planets actually formed out of a disk of material around the proto-sun. And that idea actually came out in the 18th century. It's not until this century that we've been able to actually get images of disks around other stars that really proves that idea. But Pluto doesn't fit, right? Highly inclined and also extremely eccentric orbit, right? Nothing like the other planets. Moreover, its composition is very different from those other planets. When we move out from the sun, the first 4 planets that we come out to are these rocky, metal, dense planets, like Earth. That Earth is the densest of all the planets in the solar system, right? Average density about 5.5 grams per cubic centimeter, which tells us it's mostly rock and metal inside of it. Then we go to the giant planets. Jupiter, Saturn, Uranus, and Neptune all have probably rock ice cores and then huge extended envelopes of atmosphere. Right? Jupiter and Saturn in particular are mostly hydrogen and helium, very much like the sun. Pluto, on the other hand, looks like it's mostly rock and ice, really mostly ice. And that's very different from those other planets. It seems like a very different object. Now, what we've learned is, and to give the story, give away a little bit early, is that Pluto is actually a member of another system called the Kuiper Belt, or the Edgeworth Kuiper Belt. Edgeworth was a researcher in Europe, so sometimes it's called by both names. Remember, I mentioned Gerard Kuiper back in 1948 lowered the mass of Pluto. At the same time, he also predicted that there may be other objects out there that are like Pluto, but we just haven't seen them yet. And they may form a huge repository of very ancient material. And that was, remember that was the title of my talk, is A Strange Old World. These objects are really the remnants of that phase when the solar system was forming in the first place. The inner planets, our principal planets, including Earth and Jupiter and all those other large things, have gone through a lot of evolution over the course of history. And you can just look at the surface of the Earth to see how much evolution the Earth has gone through since the solar system formed 4.5 billion years ago. These outer systems that are left out literally in the refrigerator of our solar system haven't changed much at all. So one of the interests in Pluto and other Kuiper Belt objects is that they're really a time capsule, a relic of what our solar system looked like when the planets were forming in the first place. I guess siblings of Pluto were starting to be found. And I should say my advisor, Mike Brown, was one of those contributing to those discoveries, which is why he thinks Pluto had it coming. And they're found much the same way that Pluto was found. This is a series of images now taken with a digital camera, taken over the course. The object is the image as we go through this time of 4 hours. By the way, that dashed line is an asteroid, and it's moving much faster. Right? These Kuiper Belt objects, because they're so far away, move very slowly across the sky. And over the course of the last 2 decades or so, literally 1,000 of these Kuiper Belt objects have been found, mostly by this method of looking for very, very slowly moving objects. Right? So this is a map showing the positions of known Kuiper Belt objects as of last year. You can see where Jupiter, Saturn, Uranus, and Neptune are labeled there. And then there's this cluster of different colored dots, and those different colors basically code to different kinds of Kuiper Belt objects based on their orbital characteristics. But these are a huge repository, again, of material that's way out at the outer edge of the solar system, and very much like the asteroid belt is sort of in all directions, in all places, and orbits in many different ways around the sun. Right? But these are very, very old systems, 4.5 billion years old, time capsules of the start of our universe, or sorry, start of our solar system.
What's a Trojan?
So some of the names that they come from, again, from the orbital dynamics. So if you look, it's a little hard to see with the coloring, but the Jupiter Trojans are in resonance with the orbit of Jupiter. So they're always found in 60-degree sort of offsets from where Jupiter is at any point. So they kind of orbital resonance in that, and they're clustered in that place. It doesn't actually mean they have anything. In addition, so big enough to be kind of round. Here are sort of the real large members of the Kuiper Belt, and you can see we've got Pluto there, which is the largest of that set. So it's still a superlative. It's still quite amazing, and it's also got a much more complicated moon system than these other systems. But you can see that we've found a number of worlds now that seem to have these very large sizes and have similar compositions, rock and ice, and in many cases also have moons around them. Right? But Pluto is still the biggest. Now, with all that information, Mike Brown, all right, the International Astronomical Union in August 24th, 2006, which has hereafter been known as Pluto Demoted Day, the IU voted to create a new class of solar system objects called the dwarf planets, of which Pluto is still the largest member. And that includes many of the Kuiper Belt objects I showed earlier, and also a couple of the asteroids, including Ceres and Pallas, which were very large asteroids. And I should say, Ceres is an interesting case because when Ceres was found in 1800, it was also called a planet. And it was called a planet for about 20 or 30 years until folks realized that there were a lot of these little rocky things between Mars and Jupiter, and decided to create a new class of objects called asteroids. Exactly. Ceres was demoted to an asteroid. Pluto has been demoted to a dwarf planet. It happens. Right. And it happens because we learned something new about our system. But Mike thinks Pluto is dead, which is very Nietzsche of him, but it's not dead. It's still very exciting. Okay, now, despite its change of status, it's still an incredibly interesting place because we have a lot of questions about Pluto as the signature large object of this outer Kuiper Belt system. One of the questions, of course, is what's it made out of, right? We know that the inner parts of our planets, the terrestrial planets, Earth, Mars, Mercury, and Venus, are mostly rock and metal. We can get that from the average density of the planets. And we can measure that very accurately because we can send spacecraft to those planets, measure the diameter extremely well, measure the mass extremely well. From that density, we can figure out all sorts of things, what's happening in the interiors of these planets. Pluto, it's a lot harder because it's so far away. And I'll remind you of that Hubble space image where it's just a bunch of pixels across. If you can't measure the diameter very well, and you don't know the mass very well, it's very hard to get a density, which means there's a huge range of uncertainty of what's inside of it. And it's actually particularly important for these Kuiper Belt objects because they're made of a lot of ices, which means interior, those ices are compressed and heated, which means you could potentially have liquid layers in the interior of objects like Pluto and Charon as well. And so knowing that, figuring that out is very important because, of course, liquid water is one of those main ingredients that we think life has to have in order to evolve. Right? Even with Charon, we don't even know how the material inside Charon is distributed. It might be what we call differentiated, which means the heavy stuff is moved to the center and the lighter stuff is separated out to the outside. This is exactly how the Earth is sort of situated. The nickel iron core is at the center and the crust is relatively light, mostly rocks. But we don't know if that's true for Charon or not because we didn't have enough measurements for it. And of course, we also would just like to know what it looks like. All right, and people have been speculating about what Pluto looks like ever since it had been found. And this is a picture that was an artist rendition of the surface of actually Charon looking at Pluto, done by Don Dixon back in 1979 for the cover of a book written by Clyde Tombaugh, and to sort of illustrate this sort of idea of this world. We're going to come back to this picture because it's eerily accurate. It was drawn in 1979. But the idea is that sure, there's got to be ices, maybe there'll be craters, but nobody really knew because nobody knew what the geology would be in this very distant world. No one knew what the history of this planet is, and so this was always a big question. So we started making maps, and we started making maps on fairly imperfect data. This is one of the first maps based on Hubble Space Telescope data. Remember, that was the data I worked with as a graduate student. This was created in 1996, and looks pretty fuzzy, okay? But that's, again, because you're taking data that looks like that to make that, right? So it's a little artistic license that comes in there. This is a later one using an improved instrument on HST, but again, these are extreme approximations because we can't really see the surface. What we see is how the brightness of Pluto changes over time as it rotates around. And from those brightness changes, we infer some kind of modeled map of the surface of Pluto. But clearly, this is not telling us much about the geology, about the history, and about maybe even weather or anything about the planet itself. So we really need to go there. So the New Horizons mission was originally conceived in a different form back in the 1990s in order to answer these outstanding questions about what Pluto is made out of, what does its surface look like, and what is its history. What does that tell us about the evolution of our solar system? And it's got a long history. If you're into spacecraft science, you have to have a lot of persistence, right? The original concept for this mission was developed in 1990. It's called Pluto Underground. Hugely expensive, and at the time they could not think that they could reduce the electronics to a scale where they could actually send them out, so that was scrapped. Then a very large mission, a 3,000 kilogram spacecraft was conceived called Pluto 350. That was proposed and immediately rejected as too expensive. A smaller version that was based on the Mariner spacecraft was proposed, that was rejected. And then Pluto Express was then proposed and accepted by NASA for study. And for about 5 or 6 years, that was looked at and developed, and spacecraft components were tested and instruments were developed. And then in 2000, the budget was cut. And that happens. If you look at the history of any successful space mission, there are lots of periods where the budget is cut, the mission so much work. Groups got involved, including the Planetary Society, and said we really want this to happen. It's our #1 priority to have a visit to Pluto because it's the only planet in the solar system that hadn't been visited at that point. Right? So it was resurrected as a New Horizons mission in 2001 and funded by NASA. In 2003, the NASA administrator left it out of the budget purposefully. And so then there had to be a lot of work to get it back into the budget, even though it had been accepted. And 3 years after that, that budget squabble, the New Horizons mission was launched January 19th, right? So just about 10 years to the day from today, 10 years and a month. And it flew for about 9 years and arrived last July, on July 14th, day before my birthday, by the way. And the total cost for the mission was about $700 million over the course of 15 years. Now, that seems like a lot of money. That's about $2 per American. So, thank you. All right. So, worth every dollar, worth every $2. Because this was a one shot, right? This was, sending a mission out this far into our solar system is not something we're planning on doing lots of times. And so the original concepts were very instrument heavy because they wanted to make sure they got as much information out of this pass as possible. And that was true even in the New Horizons era. So there are about 7 instruments on this spacecraft, all with different scientific objectives. A lot of the pictures I'm going to show you from here on were taken by the LORRI camera, which is the high-resolution visible camera. Basically a very long focus length camera that can take extremely sharp images. And we're going to see some of those in just a moment. There were a pair of twinned cameras, Ralph and Alice. Alice to the moon, all right? To Pluto, I guess. And so Ralph is what's called a multispectral visible and infrared camera spectrometer. It sounds like lots of things, but basically can take pictures in multiple wavelengths and stitch them together to figure out the composition of the material that's looking at. It's used very often in planetary studies here in the terrestrial system as well. And Alice is an ultraviolet imaging spectrometer. As you'll see, it was used to figure out what the atmosphere of Pluto looks like. And there is an atmosphere of Pluto, as we'll see in a moment. There were also high-energy particle detectors that were used to measure the plasma and the solar wind particles out at the distance of Pluto, because not a lot is known about the solar wind at that distance. There was a dust counter named after Venetia Berti. And one of the amazing things about this dust counter, it was built by students at the University of Colorado Boulder by undergraduate and graduates, and in fact, they still run the instrument Graduate students are doing all the analysis for this. There's no, research scientists involved. The students are doing it. And that's measuring dust particle sizes. And again, that gets to what does the solar system look like at these very large distances. And then finally, there's a radio transmitter detector experiment, whose sole purpose was to basically send radar signals back and forth between Earth and Pluto, not for communication, but for very accurate timing and position information, because that allowed us to figure out things like the mass of Pluto and Charon as the spacecraft passed through the system. Now, in order to launch this out to the outer reach of the solar system, a really fantastically huge rocket had to be used. This is the Atlas V. It's the first time, when this was launched in 2006, it was the first time that this particular Atlas model had 5 rocket boosters at the very bottom there. Usually there are 1 or 2 or 3, but 5 was used. And this was the first time an Atlas rocket had 3 stages to it. And I'll point out the 3rd stage is this tiny little piece right here called the Star 48B. It's named that because of the diameter of the sort of fuel tank is about 48 inches, which is pretty big. And that last little booster was what was needed to get the New Horizons spacecraft at the speed necessary to get it out of the outer reaches of the solar system. Remember, we're right now orbiting the sun. The sun pulls tremendously hard on everything in its system. In order to get out to Pluto, you have to put a lot of energy, kinetic energy, to get out there. So the only way that this spacecraft could make it was to have 3 different stages of rockets with a lot of propulsion. And as a result, this was the fastest launch ever from the Earth. And I think that's still true to this day, right? 36,000 miles per hour as it was leaving the Earth. And that's just enough. In fact, it wasn't quite just enough, as I'll show in a moment, to get the spacecraft out to the orbit of Pluto. I should say one thing, this little 3rd stage rocket here, just the way that the launch trajectory went, it actually made it to, it made it out the rocket. All right, let's try this. Look up at YouTube, just look up New Horizons. Amazing. Enough to make it. See this trajectory here, but 2007 in such a way that it kind of as well to get out to the outer reaches. In fact, 2 years. The movie showing an eruption on serious problems captured. Okay, coming in. Image that we're starting to actually see that shows excited when they saw. So, or passed by Pluto. Except one person will see them all. The sun is much fainter. This is actually the kind of that the mineralogy of the surface of Pluto. You see point. Montes that are very rough and modeled, we call them the Badlands. So oh, that. Basically nitrogenized. Areas. That region off to the right side there. Okay, so again, that is involved in the Pluto mission. Or no one expected to see to have geology on such a small world. The multi and then you have these. Now looking at the edge, Pluto just flew, the or something like that. Those measurements by looking at measurements. Now, appreciable fraction of the size of the planet. planet. Based on their properties, we think these mountains being not seen in a very short period of time. That is flowing. There's glaciers around the surface. Now, and even when you look in detail, so now the amazing thing about water ice and nitrogen ice doesn't sink. The glacier, glaciers.